also make recording.
Oh, okay.
So typically, it is Donald who is doing it. Okay, so very short preface is that like 15 years ago, Sam, who invited me to Shanghai region, not exactly to Shanghai, to give talks, actually to have some classes with Russian and Chinese students, right? So Pavel was there in particular.
Right.
Billy also was there.
Yes.
And there I used the following teaching method. It's called do it yourself. It means that that I somehow explain what to do, and with my help, people are creating stuff themselves. And it was not that bad. Now I want to do today the class in the same spirit with one improvement. Improvement is that things that we will discuss right now are not known yet in the world literature. So while 15 years ago or 16 years ago, it was you do it yourself just to study, what I'll try to do, say, today and tomorrow, yes, is to move this type of seminar to a research seminar. So we will do things together. So I intentionally did not went too far in it because the topic is quite new. I realized it just several months ago. Okay, so we can do it together, and as a result, not only we will understand something, but also we could publish a paper. Okay. So this would motivate you. Okay. So the only drawback of this thing is that there could be some things that I overlooked. Okay. So not all my suggestions would be absolutely proper. So sometimes I will give wrong suggestions or say wrong conjectures, okay, or even make mistakes in calculation. However, this is the price that we have to pay to work together and to go at the proper speed. Here I follow advices of Pasha's father. He says that I have to go at the proper speed. Okay? So let us try to work like this for today and tomorrow, and let us see how this would go. If we would like it, we can continue this way. Okay? If we feel that it is not going properly, we can come back to original style. What do you think about it?
Sounds good.
Good.
Dong, what's your opinion?
I agree. Very good.
Okay. Okay. So let us try. Now, So basically, I told you where we are aiming at. So we want to construct a constructive. So I will say effective theory of. So let us reduce our scope. Let us reduce it to toric maps. So this toric to toric maps is a, it seems that it's a subcategory in the in this category that I called GLSM category. Okay? So if we will be effective here, we can move here. Okay? So this should be a generalization of Divental in theory to higher dimension. Okay? Let us say beginning. And here there will be no differential geometry. Or quantum field theory. Let us work it out in a purely mathematical way. Okay? In the simplest possible context. And when we will work it out, we will later come back to Giventhal-Kim theory and see how it appears as a particular case of the general theory. Okay? So it's our goal in this. It's one of our goals. Okay? So if this is our goal, then the question is, what could be our tool? Tools would be more modern, and tools would be, of course, equivariant integration. Still, I need to say that nowadays people are replacing this equivariant integration by so-called K-theory setup. So we had not discussed K-theory setup, so equivariant integration means that you are computing equivariant volumes. K-theory setup means that you study the number of sections of line bundles, actually, on the space of maps. And one come to another if you take some limit. We will discuss it later on. But let us discuss simpler things, okay? We will discuss this later. So some people may say that the equivariant integration technique is outdated and one has to start with K-theory setup. But let me be old-fashioned here, okay? We already discussed equivariant integration, and let us do it this way. I just want to say that both Giventhal and Kim moved to K-theoretical setup. However, we would like, at least I would like to see some string theory and quantum field theory constructions, and they are more transparent and when developed in the equivariant integration setup. Okay? Okay, that's it. So I hope I will not say any general words today at all. Okay? So so what I hope we will do would be only toric manifolds of different kind, and at some moment, maybe not today but tomorrow, we will consider the issue of blow up, and the blow up that we will consider would be compatible with the toric structure, and we will later on meet psi classes. It would be not psi classes. Sorry, I have to say it.
So Andrei,
So later we will need blow-ups. However, blow-ups would be inside the toric technique. And second thing that we will meet would be psi classes. However, we would see that psi classes are nothing but equivariant parameters. So these two phenomena would lie together inside this paradigma, inside this general scheme. Okay? Now, first remark, that toric is V over, so I need to call somehow this group U, sorry, C star to the power n is a group that I need to call I'll call it T, okay?
So
Better to call it T.
and the camera focus is sort of moving back and forth. So now it's kind of very fuzzy.
Ah. So what about now?
Now it's good.
Ah. So C star over N would be called T toric. So it's actually an algebraic torus.
Mm-hmm.
So we will study this to this. So V is a vector space. And T is acting on V in a very conventional way. So V is C to the K, and T is acting here by character. Z1, ZK, Z1 is going to lambda A and 1 Z1, lambda A, let's better say, we call it not N, but Q charges, QK, ZK.
So it should be Q1A and QQKA. I mean, there should be a matrix of weights, right?
Z1,
Mm-hmm.
yes. Here is a product over A. And in order to stabilize, we have a moment map.
Mm-hmm.
So first thing is that when we study these maps, and here I'm coming back to what I discussed last time, is that I want to discuss polynomial maps, not all maps.
Mm-hmm. Mm-hmm.
So it's one thing, polynomial maps. And also here I want to have T1 external. And here is T2 external. So it means that while T, so all T's are acting this way. However, here we can have external T. So there is a maximal T acting on V1.
Mm-hmm.
So after I take a quotient with respect to T1, that is better to call gauge. I still have T1 external. So I hope that this setup is clear.
Mm-hmm.
So what is polynomial map? Polynomial maps are, of course, the maps of V1. And here I have Here we will have symmetric powers of V1. To V2. So it is clear that polynomial maps, so main issue is that the polynomial maps are also of form, a toric variety.
Mhm.
And we will see it immediately in an example, okay? Because so what we can do? We can compute equivariant volumes with respect to what? With respect to T external. That is formed from T1 external and T2 external. So parameters of T2 external would correspond to geometry of the target. Parameters of T1 external would correspond to geometry of the source.
Mhm.
In particular, psi classes would be here because it corresponds to the source. Target space cohomology would be here.
Mhm.
But everything is combined into this tool. Okay? I hope I do not need to say any more general things, and we can go directly to examples. However, I assume that this was a kind of the warm-up. Okay? Is it okay?
Sounds good.
So I'll ask Pasha because he was a student 15 years ago.
Sounds good to me.
So is the setup clear?
I think so. I think so. Mhm.
And it is new because I never heard that anyone studied this in this way.
Mhm.
Okay? So it's a novelty. This is new. So let us consider examples.
Mhm.
So the first example that I'd like us to consider in some generality would be, of course, just to have a feeling of what we are doing, CP and 1 to CP and 2.
Mhm. Mhm.
Okay, so let us do it step by step. So let us first study case when n1 equals to 1. So how should we denote coordinates? Maybe it would be good to denote coordinates here by y, here by z, or you see, in order not to, you see, they could have different indices. And if we will put index 2 here, it would lead to confusion.
Yeah.
All right? So, according to the general rule, we would like to treat it in the homogeneous way. So this will be c to the n1 plus 1 over c star. And this is c to the n2 plus 1 over c star. So on the target, we would have n2 plus 1, n2 external parameters. In so-called physics, they are called masses. So it's good to keep the names that other people are using, because when you see it in the literature, you understand what people are talking about. And parameters here would be called epsilons. And epsilon 1 time up to epsilon n1. So n1 epsilons here, n2 masses. So since we are going to take a quotient with respect to C star on the left, we should consider only, okay, so so this would be what we are going to compute. And actually, let me tell you that I do not know how the general function would look like. So we would like to compute it for degree d and take a sum over d weighted by q to the power d. So the result in this computation most probably would depend on epsilons, m's, and q. So am I right that I think that that in this setup I have only degree d here? Let us see why I have only 1 degree.
It depends on second cohomology of the target, and since it's one-dimensional, then it's 1 degree.
Yes. So at least for the case n1 equal to 1, it's true. Let us check. Is it also true if we have n1 greater than 1?
I think also you can just look at CP1 sitting inside the source. There's a CP1 sitting inside CPN1.
Yes, I think that the only invariant is degree, because I hope so. Maybe I'm wrong, but I think it's the only thing, it's the only invariant, because at least naively, if I could consider this not as a quasimap, not as a quasimap, but a map, would I consider it as a map? I would expect that that if I have such a map, cohomology go opposite way, and cohomology here and cohomology here are the modular have only 1 generator. Okay, and that's why I expect this to have degree, to have only 1 degree. However,
Oh, sorry.
it's a problem.
Now I'm puzzled because this cohomology, I mean, it's generated by a single element in the source and the target, but there is also a relation, right? That this generated raised to some power equals 0.
Yes.
So how does it work then?
So at least, so you see, it's not greater than that. So, okay, then there is a problem number 1. How to see that the only degree is d. I mean the total. I mean the total degree. By the way, is it true? And here is a special case. No, maybe I don't know the special case. So I believe it's true, but we will see. At least it is clear how to construct these things that I'll call the degree d polynomials. So let us do it. Okay? So I would say that y, so first case is n1 equals to 1, warm up. So we did it many times, but I would like to write down this example.
So I just wanted to make a remark. So I think if so we are used to the case n1 equal to 1, but if we take, let's say, n1 equal to 2, but n2 equal to 1, then I think the degree is forced to be 0. Right? Because of the
let us see. You say n1 equal to 2,
yes,
and n2 equal to 1.
yes, because of the relation in cohomology.
Ah, okay. So since we have this issue, so let us try to see what can we get in this particular case. Oh, okay.
Then you have a map in cohomology from the target to the source, but in the target we have a relation, I don't know, omega squared equals 0. So it maps.
Ah, very good, Pasha. Pasha, thank you for following the general pattern. Okay, general pattern is that we are discussing exactly those examples that are simple and maybe not clear. Since we studied the case n equals 1 and 2 general a lot, let us study this case. Okay. So we never wrote this explicitly. So we have two y's, y0 and y1. Let us try to write polynomial map. Here we have two coordinates. Okay, now I do what physicists never do, but here we would like to do it. Put indices downstairs. And z also, there will be z0, z1, z2. Because now we are in the realm of algebraic geometry, and degrees are typically upstairs in order not to mix them together, right? So why not? I'm trying to write something degree d. And coefficients k0, k1, k2. I put here not. So when I say I take sum over k with a vector, it means that k belongs to z greater or equal to 0 to the power n1 plus 1. In our case, non-negative integers. Okay, so how can I understand these C's? I did so when I have such map, I can take a quotient with respect to C star acting on source. Because things are homogeneous. So action of C star on source acts on these guys by D. Okay? So the weight of this and the weight of this are D.
Sorry, which C star acting on source? That was the gauge and the external.
The gauge, right. The gauge C star on source.
Mm-hmm.
So this is what I'd like to call degree.
But how does it correspond with the idea of the topological idea of degree? So which does something to the
Okay, but first,
topology.
so also we'd like to say that the target gauge C star acting on target
Mhm.
acts by them by one. So, Pasha, so
Mhm.
I'm in the process of discussing with you your question.
Mhm.
But meanwhile this discussion, it
Mhm.
would be interesting to to get something along the way. Okay?
Mhm.
Like these weights. So we have these C's with weight D, this with weight 1. Now now note that we have a nice space. Okay? For so I just want to say that we have very fixed weight system. D here and one here. Okay?
Seems like this space is a Grassmannian. I think it's a Grassmannian describing the two-dimensional subspace inside like a vector space of dimension n at 2 plus d choose 2.
Let us see. Okay, so there are two notations. Okay, so you see, this space is toric. Typically, Grassmannian is not toric. So it means that Grassmannian, general Grassmannian is not toric. This is toric.
Oh, this is toric?
Yes, so because we have weight here.
Yes. Wait d.
So you want to ask what are other weights? Okay.
Yes, yes.
Okay. So let us come to the question: is it toric or not? Because I thought it is toric.
Okay.
Yeah, it doesn't look like there's enough.
Grassmannian is not toric. So we'll come to Dom's question in a second, but at the moment, let us see that there are such maps. So we have the number of these caves, and it is definitely a binomial number. So
if I only consider the gauge C star action on the target, it definitely would be Grassmannian, but you're saying that we have to consider the weight D action from the source also.
yes.
And quotienting out
Yes.
the Grassmannian by that action will give you a toric. Is that your suggestion?
Yes. It's so yes, it's answer to your question. But at the moment, I see that this space of maps has definitely dimension on the space maps. Okay, so I call it maps. Okay, quasi-maps. So it's not, I don't know, vector maps. Because later on I'll take a quotient. So I have this space Vm of dimension D. And dimension of this space is, so if I clearly generalize, I say that it is n2 plus 1 times some number. It is binomial. So this has to be binomial coefficient, and okay, so it is actually it's some number BD, some number BD that depends on N1.
I think that would be the D plus N1 choose N1, I think. And
Maybe.
minus N2 maybe, but there should be a leading binomial term, and that would definitely be a D plus. D.
You see, in Russia, we had a different way to choose. So maybe something like this. So D, maybe D plus 1. Okay, and here we choose like N1 plus 1, something like this. So
Okay,
this
can you
is
make-
so this seems to be a dimension. Okay. And the weight. So the gauge weight is that so the weight of the weight of the source is the weight of the source is d. Okay. The gauge weight of the source seems to be d everywhere here, and the gauge weight of the target seems to be 1. So 2c star that are gauge source and gauge target act on this space with the weights d1. Okay. So that's why this space is C. At least that's what I feel. So it is okay. So here we have common weights. So how to so what is this space if I have c to the power n and I have equivalent quotients. So it seems that so it looks that the difference is acting by 0. So it seems that you see if one C star acts with D and another C star acts with 1, then in the quotient I do not need to have 2 C stars, right? It means that in the quotient, 1 C star is not acting at all.
So when you say quotient, you quotient by the first factor or the second factor?
So
Diagonal
So-
factor?
so naively, I may think that I need to quotient with both
Quotient with both?
because I have the C n1 plus 1 over C star, C n2 plus 1 over C star.
Okay,
So I would expect that I have to quotient with both
okay.
in this particular case. However, I see that there is one gauge C star that acts that doesn't act on this space. So that's why this space is actually what? is, so let us call is C. So it looks that this space is CP dim VMD minus 1. Conjecture 2. And I see that one C star just commutes. So how should I say it? These two C star act collinearly. Only one group actually acts. And one is not acting. Okay? By the way, this is exactly the formula that we obtained in the simplest case when n1 was equal to 1. So here we have generalization of this formula. Now, let me try.
So actually, I'm confused about CP something versus Grassmannian. So here we are writing CP something.
So you see, I determined this space. So I was not saying this Grassmannian.
No, you determined the dimension of the space, and then you wrote CP of that dimension.
No, not only dimension. I determined that this space was C to this power, and I have to quotient it by two groups: the group of the source and the group of the target.
Okay.
Now,
yeah.
Now, suddenly I see that that one of the group lies inside another of the group.
Oh, it was the same for maps out of CP1.
Yes. Still, I am. Yes, it was the same. So this gauge group, where we have degree D. So this was the group of the source. And this is the group of the target.
But then, okay, but I'm still confused about the question that I asked.
Yes, I'm coming back to this. So now I'm answering your second question. The second question is, why do I think that this space is this? It's because we have a vector space, and we need to take such quotient.
Okay, that looks reasonable.
Now I'm going to, but you may say that when we do such procedure, we also have C star in mind. So the quotient is not this, is this, and here we have C star that acts trivially. So it is conclusion. Now Now let us come to your question about how can it be. So suppose we have CP2 and here is CP1. So the question is, can CP2 map to CP1 non-trivially? So let us see.
I think you can probably even trace what happens here on the level of moment map polyhedra, like triangle going to an interval.
Yes, but so my impression is that that I can do it because look, I have a class of the point on CP1 that is a target. I can look at pre-image of the point.
And it has to be 0. So the pre-image of the class, if by class you mean Poincare dual class in H2, in H up to 2.
Okay, so let us see. So pre-image of the point, we take pre-image of the point. You say that it has to be 0.
Right, so I mean, we should be careful what we are saying here. Okay, if what we are saying is that we take a point in the target and the Poincare dual class, so call it, I don't know, omega. So it's a class in second cohomology. So it's a generator of second cohomology of the target, right? So then its pullback by the map is some class in second cohomology of the source, which squares to 0.
Okay, let us see. So map star of this omega to the point should belong to the second cohomology of CP2.
Yes.
Right. Then you say that it's not only maps of the vector spaces, it's also maps of the rings.
Yes.
Right?
Yes.
So if you intersect these two things, here you get 0. Aha. So from this, you would conclude that there are no non-trivial maps. Okay, so this is an argument.
Yes.
Now, however, I would like to consider not maps, but quasi-maps. And let us see what happens with your argument. Okay?
I mean, my argument was topological. Maybe there's something because we're considering polynomial ones.
And here we will come to the issue how maps are different from quasi-maps. Remember that in this particular example, so it's good that you put it In explicit description,
Mhm.
there are 2 points on CP1, infinity and 0. So quasi-maps are the following stuff. You have CP2, you have pre-image of infinity, and also you have pre-image of 0. One can try to define the degree as the class of the pre-image of infinity.
Mhm.
And then you can get something. Now, the question is, how does this correspond to your original argument?
Mhm.
Hmm? And answer is clear, that in the 2-dimensional case, we have a novel phenomena
Mhm.
with respect to 1-dimensional case.
Mhm.
Let us compare. In 1-dimensional case, pre-image of infinity was a point, and pre-image of 0 was a point,
Yes.
or actually set of points
Mhm.
for higher degree. And in general position, they did not coincide, and you may speak about maps.
Mhm.
And only where these pre-images coincide, you can say that no, it's not a map at that point. So in 1-dimensional case, it was a map almost everywhere on the space of maps. In the 2-dimensional case, we have a new phenomena.
Mhm.
New phenomena is that quasi-map is never a map.
Because there's always a common locus
Yes.
of the pre-image of 0 and infinity. So
Yes. So this resembles another case in lower dimension that we considered. And this is a case.
Sorry, what you're saying? I mean, there are some maps from CP2 to CP1, right? Like constant maps or.
Yes, constant maps is a constant map. No, we are speaking about maps of non-trivial degree.
Okay. So you're saying that, okay. Mhm. So you're saying if we are considering just maps, then there's only constant maps among polynomial ones, and nothing else.
in other words, the capital Y0 and Y1 we choose at the last word always have a common 0.
Yes,
You cannot avoid it. So it never be a
we
map.
can't avoid it. We
Mhm.
can't avoid it.
But there is one possibility when they are proportional to each other, they give you some sort of, I mean, the constant maps, which gives you
Yes, but it's not a map.
Yes, right. Yes. So
Because
it's quasi maps.
because it's exactly the point where you do not have evaluation.
Mhm.
Now, so it's very good that we study this, because this resembles an example.
Mhm.
It was called CP1 to CP0. So CP1 to CP0 was, of course, the space of polynomials. We can also write it down. We already did it once. C0 plus C1 Z. Okay. So we have you have in this case you have only one Y.
Mhm.
We studied this case, but we did not generalize it.
Mhm.
It was the case where we have only one Y, Y0. So in this notation, it is N0 and 1. Z0 and 0, Z1 and 1. Sorry, K.
Yes.
And we divide it by C star. We found in this case that in general position, so there was such a space.
Mhm.
And this is definitely the space of points in the source. Actually, it's of course symmetric power of the points, because because what you have here we have a degree D polynomial. It has a constant and roots.
Mhm.
And of course, polynomial is determined by the position of roots up to the permutations. So it's actually, I thought people call it Hilbert scheme. So here we have a Hilbert scheme.
So, but what
When
should
we
we
take a
say?
code.
It's n symmetric, d symmetric power of the source CP1.
It's a dissymmetric power. So let me see of the source.
Portion. Okay, symmetric.
Yes.
Mhm.
Of CP1. Yes, exactly.
Is it isomorphic to the Hilbert scheme of D points at CP1, or they are only birational?
I think it's it. I think it's it. It's exactly what it is.
Okay.
So this particular case is a Hilbert scheme, and of course, by the way, here we also have weights, and one weight is D, so it's again D1. So picture is exactly the same.
Sorry, which picture? What is the picture? Ah, okay. Yeah.
The weights.
Mhm.
We have, as far as I understand, we have D-dimensional space.
After the quotient, yes.
So before the quotient,
Before it was d plus 1 dimension.
yes. So these Quasimaps were exact. So it is CD plus 1 over C star. And there was also a hidden C star.
Mhm.
And this is nothing but the space, okay, that we with Nikita Nekrasov are called freckles. It's a case where you have only freckles, where you have Quasimaps that were never maps. And in this particular case, the external target gauge, the external target group is empty. You can see it from here. CP0 is a point. Nothing acts here. However, there is C star external on the source. And it has weight D. Sorry, there was C star external on the source. And its weight is D. So in this particular very degenerate case, we say that there is C star, so one C star is not acting. So C star gauge has weight D, okay? C star acting on the source. However, there is another C star that acts here. And this C star has interesting weight. Actually, the weight. So do you follow me, or maybe I go too fast?
So you're saying that there's also another, yes, a star external on the source, sure, and its weight depends on K0 and K1.
Exactly. But before I put this C star on the source, I want to understand this space as a space of points on CP1 source. And of course, I have a quotient by the symmetry group. One second. Алло. Неинтересно. You see, our goal is not only to compute numbers and weights. Our goal is to see the pictures of what is going on, right? So we should not just compute number like binomial coefficient or some product of some monomials. We would like to get a feeling of what is going on, right? So this space is this. Points, non-numbered, on CP1. Now it's interesting. we may start to think, what could we compute about these points? It's one thing. And another thing, how can we generalize this? This was on CP1. But we may equivalently consider, and we will do it in a second, localization here.
So these points, they can collide.
These points can collide. Why not? Roots can collide.
Yes, sure.
They are roots.
So topologically, it's an orbifold, or
Yes. So, but we are not afraid of this being an orbifold because we understand that it is very proper space. So it's this space with the action of this group. Okay, you may call it weighted space. You see, now I think it's interesting, yes, because you may start to think about it in terms of roots, symmetric group, etc. But this is a geometrical description that corresponds to the very particular case.
yes.
Particular 1 here, particular 0 here. And what we are going to study is higher dimensional generalization of this. Now, when we have not 0 here, but 1, 2, etc., we have maps in general position. And we have Quasimaps only when here is 0, here is 1. Now, here is another example. Here we have a map of CP2 to CP1, and there is Pavel's argument saying that here we have quasi-maps in general position. Actually everywhere, you see. When codimension is 0, it means everywhere. Then Pavel says that if we put here 2, then most probably in general position we will get
A usual
a
map.
map.
Yeah.
So how to draw it geometrically? You see, the science is called algebraic geometry because we can simultaneously do algebra and draw pictures. You see, sorry for my simple point of view. So when we have CP2 to CP2, here we have 3 points. I'll call them 3 divisors: D0, D1, and D2. Okay? Of course, these 3 are not canonical. Like 2 points on CP1 are not canonical. But that's what we discussed last time. Now, this is not a map if these 3 things happen simultaneously. So on CP2, we have 3 curves: pre-image, of D1, pre-image of D0, pre-image of D2.
Mhm.
Two things intersect,
Mhm.
but three things do not intersect in general. That's why in general position, we have a map. Moreover, from this geometrical picture, we have a conjecture. That in this case, codimension of quasi, okay, I'll call it strictly quasi-maps. In maps is 1.
Mhm.
Therefore, there should be now an algebraic formula.
Sorry, I'm slow. I'm not sure I understood this argument with intersection of three pre-images.
So suppose we have pre-images
Mm-hmm.
D0, D1, and D2.
Mm-hmm.
If we have a map.
Mm-hmm.
Typically, these pre-images are okay, quasi-map.
Mm-hmm.
In quasi-map, we definitely have pre-images. So these pre-images are nothing but zeros of polynomial. Like
Yes. Mm-hmm.
we have y2,
Mm-hmm.
that is,
Oh, yes. Okay. And we want a mutual zero of all three polynomials. I see. Yeah. Mm-hmm.
k0, k1, k2. So pre-image is exactly zero of this polynomial.
Mm-hmm. No, I see. I see. Okay. Mm-hmm.
So this is an equation. This is an equation for a curve
Mhm.
in CP2 source.
All right. No, I understood. Okay. Mm-hmm.
That should be look like pre-image. Okay, quasi pre-image of D2. Maybe it's better to say quasi pre-image than pre-image because it's not generally a map. So quasi pre-image is this.
Mm-hmm.
So I wrote it like this. Now let us draw three quasi pre-images. They are three curves. From geometrical intuition, it's clear that in general, they do not intersect at one point.
Mm-hmm. Mm-hmm. Yes.
Good. So in this case, we can speak about the degree.
Mm-hmm.
But to speak about the degree, it's not the only thing that we would like to do.
Mm-hmm.
We would like to see, in particular, the codimension of strictly quasi-maps inside maps.
Mm-hmm.
And from this particular picture,
Mm-hmm.
geometrically, it's clear that this codimension is equal to 1.
Mm-hmm.
We can see this geometrically, not algebraically.
Mm-hmm.
So, of course, there is a question. How to find codimension of strictly quasi-maps inside maps. And Pasha, your example
Mm-hmm.
was very instructive.
Mm-hmm.
Because here we can study this issue.
Right.
So you see, it's interesting to study CPN 1 into CPN 2.
Mm-hmm.
It's not that stupid.
Mm-hmm.
So at the moment, maybe we should take a break.
Mm-hmm. Mm-hmm.
Because now, yes, we discussed 1 hour and 30 seconds and 30 minutes. Let us have a 5 minutes break.
Okay. Mm-hmm.
Pasha, are you still alive?
Yes. 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 So far, yes. Mm-hmm.
So let us take a 7 minutes break, and
Mhm.
then we will continue until Pasha would stay alive with us. Okay?
Well, it's better to actually have a deadline rather than waiting until I drop off.
Still, okay. 7 minutes break.
Mhm. Okay. All right.
Okay. Pasha,
Да. Ага.
okay.
Ага.
So I'm back.
Угу. Угу.
Okay. So now let us continue discussing questions that that arise. So first question, I think, could be rephrased as following. So consider general Pasha question. Toric. What is the dimension of codimension of strictly Quasimaps in Quasimaps?
Угу.
So here I say toric to toric, but actually we may consider CPN1 to CPN2.
Угу.
We may also study products of CPN11, CP and L1 here. And we will come to description of this space in a second. Still, I want to show you that these questions are doable, geometrical. Yes? So let us discuss another basic example. So what is interesting, so what I consider interesting is the changing of the geometry of the source. Because mostly when people are talking about, say, toric to toric maps, they mostly fix the geometry of the target and study a lot of what happens from the target point of view. So this was studied by geometers for tens and tens of years, for decades, as people say. The geometry of the toric, if people map a point, or if people map CP1.
Угу.
So now let us speak a bit on the geometry of the source. So how can we generalize source? Just to see what's going on. So, simplest possible example, CP1 times CP1, say to CPN. So one of the way to treat this space, I would say naively, is something where we do not expect generalizations. We can say that map of CP1 times CP1 into CPN should be a pair map CP1 to CPN. We can call it first times map CP1 second to CPN. All right? However, since what we are studying are not maps, but rather quasi-maps, it will be better to redefine this.
Actually, I'm not sure I understand this formula. So, I mean, maps from a product is not a product of the space of maps.
What is a product of the space of maps?
No, I mean, if you take the product in the target, then yes, the mapping space is a product of the mapping spaces. But if you take a product in the source, then it shouldn't be.
So how we should speak about it?
Well, it's something much larger in principle, right? Like maps from a
Sorry,
square.
maybe I got it wrong. So how to say it properly?
Well, in some sense, it's tensor product, right? But, or
Yes. So yes. So proper things. I think that functions on the space of maps.
oh
Maybe this.
no, that's
Maybe
still
this would be proper.
okay. Functions on CP1 cross CP1 is the, I guess, tensor product of functions on CP1 times functions on CP1.
Yes.
That's fine.
So the same. So the same, I think, happens.
No. That's that doesn't sound right either.
Okay. So let us get it correct.
And what you can do with the product in the source is you can adjoin it. So maps from CP1 cross CP1 to CPN it should be the same as maps from CP1 to maps from CP1 to CPN.
So let me see. Let me see why I think. So would it be not CPN, but a point? No, but R. Say R.
Yes.
This would be true.
No. So well, first of all, oh, I can't see anything now because the focus changed. The camera focus changed.
Oh. Okay. Focus.
Yes. Yeah. So if the target were R, then maps from CP1 cross CP1 to R, let's say in as smooth maps, that would be the tensor products of maps from CP1 to R by CP1 to R, not taking additional space of functions, just maps.
Okay. Okay. So in any way, I am not even going to use it. Okay. Because we should so the rule of the game is that we should try to consider it in terms of Quasimaps, anyway. So what is it?
Andrei, focus changed again. It's impossible to see.
Thank you. Let me reload the camera.
Oh, it
So
changed.
now,
Oh, it's jumping back and forth. It's okay. This second, it's okay.
so I need to write more. So to keep focus on. So this is actually this map. Pn2 plus 1 over C star. So here we have a novelty. So first time we have a novelty. Now we have C star square here. And of course we know how to write down these maps. By the way, they'll have by degree.
Yeah.
Because in this case, it will be Z0 K1, Z1 K2, sorry, K0 K1. So this would be dependence of Y on Z0 Z1. But there should be also dependence on W0. W1, right? L0, L1. And here I have this coefficient. C K0, K1, L0, L1. And this is for YA. A is going from 1 to N2 plus 1. Or actually from 0 to N2. In standard notation. In here I have a sum over K and L. And now I have extra condition. So now I should again have condition on degree. K0 plus K1 should be D1. L0 plus L1 should be D2. And I'll call D1 and D2 multi degrees. Well, that's it. So I have this space. Once again, this space, so I can compute the dimension. of this space. It, of course, has dimension. How to say? I call it V quasimap. V by V quasimap, it's a vector space that we need to take quotient of.
Mhm.
It has dimension here, d1 plus 1. Dimension here, d2 plus 1. Dimension here, and 2 plus 1.
Mhm.
And we have the gauge group. So this is source, and this is target. So expected dimension is this one minus 3. I think once again, we have weights.
Mhm.
So weights are, so all these things have weights that are the same. D1, D2, and 1.
Mhm.
So what can we say about this group? Everything here has the same weight.
Mhm.
Okay?
Mhm.
That's why we actually have minus 1 here.
Oh, minus 2.
Okay?
Oh, minus 1. I see. Yeah. Okay. Yeah.
They all have the same weights. So it is funny. It's funny to see that the target gauge group is strictly inside the source gauge groups. So it has minus 1. So this looks like, and once again, conjecture. But you see, so if we look at the weights, so if we look at the weights, it is like CP, this number, some n, and here we have 2C star that act freely.
Sorry, I didn't understand the last thing you said. What?
So these are the weights.
Yes.
So to take quotient
Mhm.
with respect to 3,
Mhm.
with respect to product of 3 gauge groups,
Yes. So okay, C star times C star acts not freely, it acts trivially.
yes. Sorry, I said, yes, it acts trivially, yes.
Mhm.
So now there is a problem. Question.
Mhm.
So the question is, when I'm treating it this way, I assume the standard moment map. And this standard moment map is saying that not all C vanish simultaneously. So it is one. Equation. What could mean other moment maps?
No, but here I don't understand. If there is effectively only one C star acting, then there is only one moment map, right?
Yes. Yes. Yes, but maybe here we may choose some other moment maps already for this.
This I don't quite understand. I mean, you already listed the weights.
I'm in the following. When you have, so it's a good point to discuss. Okay. When you have a vector space and set of weights, this itself does not determine the quotient.
But I mean, in the moment map, you just tried it using the same weights, or what is the choice there? I mean, you write down a Hamiltonian, right? Using the same weights.
So you are right. I think you are right. If you do it this way, so you want to say that if all weights are positive, and in our case, all weights are positive, you say that basically there is no choice to have other moment map. So either something could collapse to a point. So maybe this question is premature, okay? Maybe I asked it too early, okay? So in this case, it seems that since all weights are positive, there is no way to play. So maybe later on we will have this issue of other moment maps. And I hope I would be able to show you this in a moment. Now you see that for these Quasimaps, I always have some gauge group. Okay, it's finite dimensional, so don't be afraid. It's finite dimensional gauge group that is here. So you may ask, is it what? Did we expect this? I mean, did we expect that there is such a map? And
that there exists which map? Sorry.
So in this particular example, you see, there is C star square that acts trivially.
Right.
So the question would be, could we expect it from the very beginning? So, in particular, would there be no first, no second CP1? You can do all the same. Just ignore everything related to the second CP1, to this CP1. And you will have just C star. So for the case of CP1 times CP1, we have C star squared.
Mhm.
So let us recall what did we got for the case of. So we may ask, what was this group for the case of CP2?
Then there was a single C star acting trivially, right? And
Yes.
so it was the source gauge group that we absorbed into the target gauge group, or the other way around, I don't know.
Mhm. However, we may ask, yes, it was the source gauge group.
Mm-hmm.
Okay.
Mm-hmm.
So let us see what is this great difference between CP1 times CP1 and CP2.
The toric denominator, so the...
Yes. But we may try to see, could we see it from this factor?
Mm-hmm. Well, you could say it's the rank of H2 of the source.
I think it's not the rank of H2 of the source.
Mm-hmm.
But anyway, there is this group. So here we had C star. You see, I'm asking this because CP2 and CP1 times CP1 were just two different source variables.
Mm-hmm.
So here we come to the following question that's again important in the high dimension of the source.
Mm-hmm.
In the contrast with one-dimensional case, there are many toric varieties.
Mm-hmm.
Of dimension 2.
Yeah.
So let us consider, just as an interesting example, another typical variety that is a toric variety.
Mm-hmm.
And this variety would be CP, I don't know what example would be best to consider. Say CP1 times CP1 blown up. At 0, 0 point. You see, these maps, so what we studied at the moment, so these quasi-map spaces are simple. Now, what can we say about quasi-maps of this? So, let us describe this CP1 times CP1 blown up at 0, 0 point. So, so actually, when we blow up a 0, 0 point, we have more interesting picture. I think that we have this. And we have a quotient of a C star cube. Let us construct this. So, so what I'm writing down, so what is this picture all about? So let me recall how you can get this polyeder. It's, of course, it's a very particular example. So let me recall what Gorodentsov was teaching us. He was teaching us the following. Suppose we have a vector space V. Suppose we have charges. Qi. So Hamiltonian A are this. So we have V over C star to the power K, Vn. So he said Cn. So I was going from 1 to n. And A is going from 1 to K. So we form these Hamiltonians, and we pick up constants in the moment map. So he said, we have to solve this system of equations and divide by u1 to the power k. And in this way, he said, in general position, you will have n minus k dimensional variety. Okay? Complex. Then he said, look, guys, it is very interesting to consider the following coordinates called r. So what I'm explaining could be found in papers of Waffa and collaborators of 90s. So people studied it in physics too and wrote it in a very simple way. Because, you know, physicists are simple-minded. So, and I don't know mathematical book where it is explained as simple as there. So I'll repeat it in this way. Now, these equations are linear, so we can easily solve them. However, there is an extra condition. What is the extra condition on Ri?
Positive.
Exactly. Non-negative. That's why you have the system of equations and equalities. And that's how we get this polytope. Now let us apply this knowledge here. So how do we understand CP1? R1 plus R2 minus C equals to 0. R1 is positive, R2 is positive. So it's better to take C positive and this is CP1. Of course, you need to take quotient with respect to the angle. So similarly, you can get CP1 times CP1. R1 plus R2, and here is rho 1 plus rho 2 minus gamma equals 0. So this is definitely a square. Now, how to cut out this piece? it seems that we need to have another R. And we need to look for a condition like, I think, row 1 plus row 2. So let us try to see how to get it. How to cut out. So let us first play with cutting out not a half plane from the plane. Okay? Let us cut out half of the line from the line. So let us play. It is CP1. I would like to cut this thing out. How to do it? Pasha, do you remember how to cut this thing out?
Nope. But we probably need to start with the definition of what is a blow up.
This would be a blow up.
No, I mean, this is sort of trying to claim the answer. Cutting out a corner is an answer to some question. So, I mean, there's a definition in terms of equations. What is a blow up?
Okay, so let us do it from the opposite side. Okay, then this would be the question, and let me follow Pasha's suggestion. Okay, so suggestion would be to follow your example, get it, and then come back to this issue. Okay. So in this way, in this case, it would be easier to understand blow up. Let us start with blow up of c square at a point 0, 0. So of course, this would be a quotient, right? So we will apply everything here, all this technique here, okay? So original definition from the complex geometry. There is a point, and there is another point with coordinates z1, z2. Suppose that z1, z2 is different from 0. There is a single complex line that could connect this 0 and z1, z2. Now, we would like to keep z1, z2 everywhere outside this point, However, exactly at this point, we would like to keep not z1 equal to 0 and z2 equal to 0, but rather this complex plane, complex line.
Mm-hmm.
In this way, when z1 and z2 would hit 0, we will get not a point, but a CP1 of complex lines.
Mm-hmm.
So now it means that that we would better get the following coordinates, something three-dimensional, such that our points would have coordinates z1 times u and z2 times u. So we will have coordinates z1, z2, and u.
Mm-hmm.
And when I say and then I think so. Let me see. Do I get it correctly? I think not. I think I have to do it like this. So, or even like this. So I want the following. I actually want, just let me see. I want to understand that z1 over z2. I forgot for a second the standard way to do it. So z1 times z2 should be fixed when z1 and z2 simultaneously go to 0.
Mm-hmm.
So how to parameterize it? In the simplest possible way. Well, let me see. Maybe this would be okay. Something like this. In this way, the limit when z1 is going to 0 and z2 is going to 0 should correspond to u going to 0. So it's one of the way to understand it. So let me see. You see, I am So there are several ways how to describe it this way.
I think there is some standard way to describe the blow-up when you adjoin two more coordinates and you are writing down some surface in C4. Or
Yes, yes, you see. So maybe I'm wrong trying to describe it in terms of one extra coordinate, but you see, when you see, I don't want to describe it in terms of the surface.
So you want a quotient and not equations.
You see, I want to. You see, I want to describe it, and I know that there is a way to describe it in terms of one extra coordinate, adding one extra gauge symmetry, because I know the moment map picture. Okay. You see, since I am lazy, so since I cannot remember the complex picture, let me make the moment map picture that I know better. Because you see, this I know better, so I can reconstruct what is going on easily. So what I remember at the moment, you see, I remember at the moment that to take blow up means to do this. So what do I mean by writing this picture? I mean the following. Such picture typically occurs. So let me first motivate this picture. So instead of 0 here, I have a CP1 of directions.
So it's like x plus y minus z equal greater or equal to or equals 1.
Exactly.
Yeah.
Exactly. So this is something that I will get you see, here I have the intersection of the half plane with the plane, so it's better to write it in another way. So here I have R1, R2, and R3. And I think I need to study the plane like this.
Yes.
And I'd like to intersect this plane with this octant. So how do I do this? Depending on C. So for me, it's important that here the sign is minus. So depending on, well, so totally, where here the sign is minus, and also R3 is positive.
Mhm.
So now let us see. Well, let me see the choice. When C is positive, then I have a condition that R1 plus R2 is strictly greater than C.
Mhm.
And that's exactly what I need.
Mhm. Yeah.
So the intersection of this plane with the octant is such that when I project it to R1, R2 plane, I get exactly this condition.
Mhm. Mhm.
And I want to say that this is a blow up. So how can I foresee positive? So first of all, what does it mean? Let me come to this picture. Since we are doing examples, so we have three coordinates,
Mhm.
Z, Z1, Z2, and extra coordinate, W. So we see that the Hamiltonian is Z1 squared plus Z2 squared minus W squared.
Mhm.
So we have C cubed
Mhm.
with the weights 1, 1, minus 1.
Mhm.
And we take a quotient with respect to C star.
Mhm.
Now, the quotient space would be this, together with the U1 vibration here.
Yeah.
But now we need to understand in which sense this is a conventional blow-up.
Mhm.
In terms of so it's clear that Z1 and Z2 are not invariant coordinates with respect to the C star. So what are invariant coordinates? Capital Z1. Okay, so I thought it was correct. Is an invariant coordinate. Capital Z2 is also an invariant coordinate.
Mhm.
So now I see what's going on. So before blow up happened,
Mhm.
I thought I had coordinates Z capital 1 and Z capital 2.
Mhm.
So from coordinates Z capital 1, Z capital 2, I went to three coordinates, Z1, Z2, W.
Mhm.
So that's what conventional blow-up is.
Mhm. Mm-hmm. Mm-hmm.
Okay?
Mm-hmm.
So old Z1, Z2 were definitely invariants of the section.
Mm-hmm. Okay.
However, interestingly, that there was an interesting point, omega equal to 0. It was a point where Z1 and Z2 both went to 0.
Mm-hmm.
Okay? However, there was something that is left, the ratio of small Z1 and Z2. Now let us see this moment map.
Mm-hmm.
Small omega going to 0 was the old position of or naive position of Z1 capital, Z2 capital going to 0. If omega is 0, then these guys equal to 0. However, we see from this moment map that omega equal to 0 means R3 equal to 0, of course.
Mm-hmm.
But it means that R1 plus R2, RC, that is positive.
Mm-hmm.
So it means that when omega equal to 0, so old coordinates were 0, new coordinates, Z1 and Z2, are not 0. And there is a piece in the quotient.
Mm-hmm.
R1 plus R2 equals to C, this one. That corresponds exactly to previously Z capital 1, Z capital 2 equal to 0.
Mm-hmm.
So here we have this CP1. So this is what blow up is.
Mm-hmm. So, Andrei, I would like to decouple.
Okay. So so we will continue tomorrow.
Mm-hmm.
Okay.
Mm-hmm.
So summarizing, we will continue study of Quasimaps
Mm-hmm.
as a manifold. Okay, so let us see what we are studying. Quasimaps as a manifold with G target external times G source external action.
Mm-hmm.
So we are finding what is this manifold, what is this action.
Yeah. and we want ultimately the volume.
Yes, automatically getting the volume, automatically see that sometimes these Quasimaps is actually contain this C star. Okay.
But it doesn't really affect anything, or I mean, this is an invisible C star with zero weight, right?
Yes. Exactly. So we need to keep it separate. If it has a zero weight, we need to keep it separate. So we do it. Last thing, we do it example after example, asking questions. So we study example. We ask question. We answer to this question, and we get more knowledge. We get more knowledge at the moment when we ask questions, because example is in our mind. It's not that we put all axioms in the brain and try to find example. We do it in opposite way. Okay? So in this way, so I think that in this way the knowledge would come in better. From examples that you generate. Okay? From your questions.
Yeah, thank you. This is very, very interesting.
Okay? So, Dong. So,
Yes.
How do you feel about this way of discussing things?
Well, I'm very happy to see elementary but non-trivial examples. So I'm
Yes,
really,
it's
really
my goal
happy.
to give examples both elementary and non-trivial.
I see.
But the best thing would be if you generate it. So your question is it a Grassmannian?
So
How it
okay,
is
I will
related?
put it this way. I'll put it in this way. I want you to answer this question tomorrow. So you
Okay.
said that the space of Quasimaps is a toric variety, and I agree that the space of Quasimaps do have a huge bunch of circle action. I agree with that, but I'm not sure that it is really a toric variety.
Yes, I think you are right. Here I think you are right. It has a bunch. Thank you. It's my mistake. You see, it has a lot of toric actions, but is not a toric variety. You are right.
So,
Yes.
so something was CP of some very large dimension, but something else is a Grassmannian. So which one is a Grassmannian and which one is a large CP?
So we will try. Okay, so it is a Dong assessment. So that this space has a lot of C star actions.
Yes.
But the amount of these C star actions is not enough to make it toric.
Yeah, that's what I'm worried about.
Case,
when you say this space, which space? I mean, I think we agreed that Quasimaps from, I don't know, CP2 to CP1 or whatever example we were looking at, that was CP of some degree, no?
Yes, but the statement that Dong made is that despite they are projective space, the potential toric structure is not coming out of this.
I see. Oh, I see. Okay.
Yeah, that is what I'm pointing out.
Okay.
Yes, and that's why maybe considered as auxiliary, or it's not clear from the construction that they are toric.
Yes, but I'm still fine. We have a lot of torus actions, so we can do fixed point localizations.
Exactly.
Like equivariant volumes. So I'm happy with that. Just Just to make
Yeah.
sure that it's not a toric variety.
Mhm.
Yes, yes. So you see, I told you that when we do it this way, it becomes a research seminar.
Mhm.
Okay.
Okay.
So let us see the simplest example. When it is toric, is not toric, or how to see that it is not toric. Okay. And let us see simplest example.
Okay.
Okay.
All right. So,
Good.
Okay.
Andrei, are we on for the 5:30 Moscow time?
Sure, Pasha.
Okay.
Sure.
Okay. Then I should have some sleep.
I'll
before that.
tell you interesting things that I found.
Right. Uh-huh. Okay then. So thank you.
See you.
See you.
See you.
Mhm. See you. Mhm.
Goodbye,
See you tomorrow.
everybody.
Thank you for watching.
Bye.